Every story about artificial intelligence starts the same way, with a question. Can a machine think? That question is older than the computer chip, older than the transistor, and it has pulled some of the sharpest minds of the 20th century into a decades-long argument that is still not fully settled. I'm Marco, and this is a new video format of Bowl of Data. For the next few minutes, we're going to walk through that argument, from a wartime mathematician's thought experiment in 1950, through 2 long winters of broken promises, to the single research paper in 2017 that quietly rewired everything, and the diffusion models now generating images out of pure noise. This is the history of artificial intelligence, checked fact by fact against the historical record. No hype, just what actually happened and when. The first building block arrived in 1943, before there was a working computer to run it on. A neuroscientist named Warren McCulloch and a mathematician named Walter Pitts published a paper called A Logical Calculus of the Ideas Immanent in Nervous Activity. In it, they modeled a single brain cell as a simple switch. It takes in signals, adds them up, and fires only once a threshold is crossed. That tiny idea, the artificial neuron, is still, in modified form, the basic unit inside every neural network running today. 7 years later, in 1950, the British mathematician Alan Turing published Computing Machinery and Intelligence. Turing sidestepped the messy question of what thinking really is and proposed something testable instead, a game he called the imitation game. A human judge holds a text conversation with 2 hidden participants, one human, one machine, and tries to guess which is which. If the machine fools the judge often enough, Turing argued, we should stop arguing over definitions and just call it thinking. We now know that as the Turing test, and it framed the debate for the next 70 years. 6 years after Turing's paper, in the summer of 1956, 4 researchers, John McCarthy, Marvin Minsky, Nathaniel Rochester, and Claude Shannon, organized a 2-month workshop at Dartmouth College in New Hampshire. Their funding proposal to the Rockefeller Foundation contained a phrase nobody had put in writing quite that way before: artificial intelligence. The Dartmouth workshop didn't produce a working system, but it did something arguably more important. It gave the field a name, gathered its founding generation of researchers in one room, and stated its founding bet in plain language that every feature of human intelligence could, in principle, be so precisely described that a machine could simulate it. That bet is still the one the entire field is making, whether the tool of choice is a handwritten rule or a 100 billion parameter neural network. 2 years after Dartmouth, in 1958, psychologist Frank Rosenblatt built on the McCulloch-Pitts neuron and created the Perceptron, an algorithm that could learn to classify patterns by adjusting its own weights from examples, rather than following rules a programmer wrote by hand. Rosenblatt didn't stop at software. Working out of the Cornell Aeronautical Laboratory, his team built the Mark I Perceptron, a physical machine with a 400-pixel camera-like input, wired up so it could actually learn to tell shapes apart, and it was publicly demonstrated in the summer of 1960. Around the same time, in 1959, an IBM researcher named Arthur Samuel coined a term of his own while writing about a program that taught itself to play checkers. He called it machine learning and defined it simply as giving a computer the ability to learn without being explicitly programmed for every case. By the start of the 1960s, artificial intelligence had a name, a founding conference, a working learning machine, and a term for the process driving it. What it didn't have yet was a way past that machine's limits. Those limits showed up on 2 fronts. In 1966, an MIT computer scientist named Joseph Weizenbaum built ELIZA, a program that imitated a psychotherapist by matching patterns in a user's typed sentences and reflecting them back as questions. ELIZA understood nothing. It was pattern matching dressed up as conversation, but Weizenbaum was reportedly unsettled by how many people treated it as if it truly understood them. 3 years later, in 1969, Marvin Minsky, one of the Dartmouth organizers himself, co-wrote a book with Seymour Papert called Simply Perceptrons. The book proved correctly that a single-layer perceptron, the Rosenblatt-style network everyone was excited about, mathematically could not solve a basic logical problem called exclusive, or where the output should flip if exactly one of 2 inputs is true. Multi-layer networks could get around this limitation, but nobody had a practical way to train one yet, and the book was widely read as proof that neural networks were a dead end. Funding for neural network research collapsed through the 1970s. Historians now call this stretch the first AI winter, a pattern that would repeat: inflated promises, a hard technical wall, and the money drying up. While neural networks sat in the cold, a different approach kept AI funded through the 1970s and into the 1980s. Expert systems, programs that encoded a human specialist's knowledge as a long list of handwritten if-then rules. Mycin diagnosed bacterial infections, Dendrol analyzed chemical compounds, and for a while these systems were treated as the future of the field, until their brittleness caught up with them. A rule-based system only knows what its authors thought to write down. It cannot learn a new pattern from data, and maintaining thousands of interlocking rules eventually became more expensive than the problems it was solving. Then in 1986, the pendulum swung back. David Rumelhart, Geoffrey Hinton, and Ronald Williams published a paper in the journal Nature called Learning Representations by Backpropagating Errors. It laid out a practical way to train a multi-layer network, the very thing Minsky and Papert had said nobody could do efficiently, by pushing the network's errors backward through its layers and adjusting every connection a little at a time. Backpropagation didn't make headlines outside the field, but it quietly reopened the door that had been shut for almost 20 years. The next big public moment for AI wasn't a neural network at all. On May 11, 1997, IBM's chess computer, Deep Blue, won the deciding game of its rematch against reigning world champion Garry Kasparov, the first time a computer had beaten a sitting world chess champion under standard tournament conditions. Deep Blue won by brute force search, evaluating hundreds of millions of positions a second, not by anything resembling learning, a useful reminder that raw computing power and machine learning are not the same story, even though they end up intertwined. The learning story kept building quietly in the background. In 2009, Princeton researcher Fei-Fei Lai and her team published ImageNet, a database of millions of photographs hand-labeled into thousands of categories, built to give machine learning researchers something they'd never really had: a large, clean dataset to train and test on. Starting in 2010, ImageNet became the basis of an annual computer vision competition. And in 2011, IBM returned to the spotlight with Watson, a question-answering system that beat the two best human champions on the quiz show Jeopardy, this time using statistical language processing across huge bodies of text rather than hand-coded rules. The dataset needed one more ingredient to change everything: enough raw computing power to actually train a large network on it. That arrived in 2012 when three researchers, Alex Krzyzewski, Ilya Sutskever, and Geoffrey Hinton, entered that year's ImageNet competition with a deep convolutional neural network, later named AlexNet, trained on consumer graphics cards instead of specialized supercomputers. AlexNet didn't just win, it crushed the field, cutting the competition's error rate by roughly 10 percentage points in a single year, a jump nobody had seen before. That result is widely treated as the starting gun for the modern deep learning era. Within a few years, neural networks went from a niche technique to the default approach across computer vision, speech recognition, and beyond. The clearest public demonstration came in 2016 when DeepMind's AlphaGo defeated Lee Sedol, one of the strongest Go players in the world, in a televised match in Seoul. Go has vastly more possible board positions than a brute force search like Deep Blue's could ever handle, so AlphaGo's win, built on deep neural networks trained through self-play, showed the new approach could handle a kind of complexity the old approach never could. All of that deep learning progress up through 2016 still relied on architectures that processed language one word after another, which made them slow to train and forgetful over long stretches of text. In 2017, 8 researchers at Google, Ashish Vaswani, Noam Shazir, Nikki Palmer, Jakob Uskorate, Leon Jones, Aidan Gomez, Lucas Kaiser, and Alia Polisakin published a paper with a blunt title: "Attention is all you need." It introduced the transformer, an architecture that dropped word-by-word processing entirely and instead let the model weigh the relevance of every word in a passage against every other word, all at once, using a mechanism called attention. That single design choice made the models dramatically faster to train at scale, and scale is exactly what came next. In 2018, 2 transformer-based systems arrived within months of each other. Google's BERT, tuned to understand language by reading text in both directions at once, and OpenAI's GPT, short for Generative Pre-trained Transformer, tuned to generate language by predicting one word at a time. OpenAI followed up in February 2019 with GPT-2. Then in May 2020 with GPT-3, a model with 175 billion parameters that could write coherent paragraphs, answer questions, and even produce working code from a short prompt, all without being specifically trained for any one of those tasks. The core idea driving all of it traced straight back to that 2017 paper, attention applied at a scale nobody had tried before. While language models were scaling up, a parallel breakthrough was happening in image generation, built on a completely different idea: noise. In June 2020, researcher Jonathan Ho and colleagues published a paper on denoising diffusion probabilistic models, which train a network to do one narrow job extremely well: take an image that's been progressively corrupted with random noise and predict what noise was added, step by step. Run that process in reverse, starting from pure random static and gradually removing predicted noise, and the network can generate an entirely new, coherent image from scratch. OpenAI applied a related approach commercially first, releasing DALL-E in January 2021, a system that turned text prompts directly into images, then DALL-E 2 in April 2022 with sharper, more photorealistic results. 4 months later, in August 2022, a research collective released Stable Diffusion, and unlike its predecessors, it was open-weight, meaning anyone could download the model and run it on their own hardware. That openness is a big part of why, within about a year, diffusion-based image generation went from a research curiosity to a tool millions of people were using directly. The same underlying trick, denoise the noise, one step at a time, running on ordinary laptops. Language models and image models had been advancing for years inside research papers and developer tools, mostly out of public view. That changed on November 30th, 2022, when OpenAI released ChatGPT, a chat interface built on top of the GPT 3.5 model, as a free public preview. It wasn't a new architecture, everything under the hood traced back to that 2017 Transformer paper, but wrapping it in a conversational interface made the capability legible to millions of people who had never used a language model before. The app reportedly reached 1 million users within 5 days. A little over 3 months later, on March 14, 2023, OpenAI released GPT-4, a larger, multimodal successor that could accept images as well as text as input. What had started as a wartime mathematician's thought experiment about whether a machine could fool a human judge in a text conversation had, 73 years later, become an actual conversation millions of people were having every day, running on the descendants of a 1943 model of a single brain cell. So where does that leave the question we started with: can a machine think? The honest answer is that the field never really settled it. It just kept building more capable systems and moving the goalposts every time one of them cleared the old bar. From a 1943 model of a neuron, through 2 winters of broken promises, to a 2017 paper about attention and a 2020 paper about noise, every step in this story was smaller and more specific than the mythology around it suggests. That's usually how it actually happens. Thanks for listening to this history of artificial intelligence.